All right, so before we get started today on what I believe to be an extraordinarily important lecture, so important that I actually brought notes, so I'm not just going to wing it this time. I would like to talk to you guys about in-class assignments because I believe we had a little talk about me returning them and all that kind of stuff on Wednesday. And I don't want to say that I necessarily pushed back on it, but I'm not excited about that idea because it involves me doing work. So what I've done here for in-class assignment number 11, which is for today's in-class assignment, is I've put up an online submission portal that is due at the end of the quarter. So what I'm going to ask you guys to do is, if you want to receive your in-class assignments back, don't turn them into me physically, make a digital copy and upload them there so that I have a record that you did them, okay? I am making the due date for this, and I'm going to update it for all of the ones in the past and all that kind of stuff too, because people are kind of slowly trickling in and giving me some old ones and all that kind of jazz. I'm going to make them all due on the last day of the quarter. Now, I am absolutely aware that the solutions get shown to you guys. Notice that little lock symbol, I have them automatically set up to show them to you at 5 p.m. on the day that we cover them. I'm not going to change that by any shape or form because I think it's very important that you guys get to see my solutions and how I approach problems and all that kind of good stuff. So you may be saying to yourself, but Dr. Hartman, people could cheat and they could like just copy down the solution and all that jazz and then turn it in. You're 100% right, but this is a participation grade, okay? I would absolutely encourage you guys to try to work the problems yourselves since I'm allowing you to turn them in at any point before the end of the quarter. It does you no benefit whatsoever to cheat on these and not understand how to solve the problems because you're being tested on it. So yeah, I mean, you can 100% get by writing down my solutions and then regurgitating them back to me and then go to the test and fail the bejesus out of it. Or you can try and not fail the bejesus out of your exam. So that's my thoughts on the matter. Does that seem like a reasonable solution to the I don't want to be involved with doing something else and returning stuff to you? Okay. All right, everybody seem legit on that. All right, so I do need to go back and set up the other ones and all that kind of jazz. But for those of you that have turned in these homework 10 ones, or excuse me, in-class assignment 10s, if you want to pick them back up and submit them digitally so that you have your physical copy, by all means, come do that. All right, so today we are going to be talking about inductance just as soon as I find my notes in this here big binder of randomly collected notes. Capacitors will be on Monday. So I'm doing inductors first because your homework assignment is about inductors. And then we'll do capacitors on Monday because that's when your homework assignment on capacitors opens up. Where the hell are my notes? There we go. I have these organized in such a way for when I redo it, when I teach them both on the same day. So I have to get a little better. All right. So inductance and inductors. So I want to first talk about what an inductor looks like because it's actually critical to how it behaves, okay? And so generally speaking, we kind of have two options here for what an inductor may look like. Our first option is a cylinder like so, about which we wrap a wire. And this wire, when carrying some current I, causes what's called a magnetic flux to appear in the cylinder. So this green stuff is magnetic flux. Our wire has a specific number of turns, which I'm just going to call N turns. And this type of device is what's called a solenoidal inductor. Our second option, and I'm going to pre-apologize for how crappy this is going to look, but I'm going to do my best. Is a toroid, or for the layperson, a donut. So we have this donut of core material, typically ferromagnetic in nature. And just like our solenoidal coil, we take a wire, and we wrap our donut like so, where if our current I is flowing in like this, we wind up with magnetic flux circulating around the donut like so. So this is still magnetic flux. There are still some number of turns in the wire and all that kind of stuff. And this guy is a toroidal inductor. So we could summarize this by saying that an inductor is a two-terminal electrical component consisting of a coil of wire wrapped around a usually magnetic right? So, does anybody have any ideas where inductors might be used in a practical application? So, magnetic flux is the magnetic field lines that are bounded by a particular surface. In this case, the surface is the cylindrical cross-section of the solenoidal inductor. So I'm going to just try to draw this cross-section with dotted lines like this, and a similar cylindrical cross-section of the toroid. So the magnetic flux is the magnetic field lines effectively multiplied by that area that bounds it. These ferromagnetic cores have very, very low what's called flux leakage, which means they concentrate the magnetic field to be constrained to the interior of the inductor. Okay, so they do not shoot out by any stretch of the imagination. All right. So I repeat my original question. Where do you think inductors get used? Anybody have any thoughts? Anybody ever opened up anything electronic and seen an inductor? It looks like a coil of wire wrapped around something. I thought I literally just said that. In a doorbell? Okay. Inside of a relay? Absolutely. That's something that you learned about in your Engineering 120 series. Ian? You know, I'm not sure on that one. Honestly, I bet they do have some inductors in there, but that's not something that I would typically associate with an inductor. Right.
When it's magnetized, it closes another loop that allows a smaller current to toggle a larger current.
So that is part of what a relay does, yes, but that is not part of what an inductor does. Okay. So another place that inductors are used is electric motors. They're a huge portion of electric motors. Probably my favorite place that inductors are used are in electric guitars. The pickup of an electric guitar is nothing more than an inductor with lots of magnetic core material. And so what it does is it magnetizes the string. And as that string vibrates, the coil picks up that changing magnetic field of the magnetized string and creates a voltage signal, which then gets amplified. And that's why we have Metallica and Slipknot and all that kind of good stuff. Okay, so I'm a big fan of inductors. Probably, I know this is a nerdy thing to say, but it's my favorite circuit element. Okay, inductors are where it's at as far as I'm concerned.
Do you like it?
Let's keep it circuits related. So what does an inductor do? Inductors are used in electrical circuits as a form of temporary energy storage. That's critical to their behavior, right? So for those of you who have taken Physics 202, this should be largely a review. But if we have a current carrying inductor, right? So let's say if we have a current carrying conductor, so we literally just have a section of wire through which some current I is passing, right? This current I could be a constant value or a DC current, or it could be a time varying current. Either case, what's going to happen is that the wire will be encircled by magnetic field lines. And they are going to flow according to the right-hand rule. They're going to be kind of coming out of the surface. So they're going to start here and come out, and they curl around the wire like so. So that's true for literally any and every current carrying wire. It produces a local magnetic field. When we coil the wire, what we're doing is we're concentrating that magnetic field within a bound surface, generating magnetic flux. The magnetic flux that does not look like a C, it looks like an E, I apologize. Generated by coiling the conductor is the energy storage mechanism. And we'll get into the math behind that shortly. This magnetic flux is dependent on the amount of current that passes through the coil amount of current that passes, sorry. As this mathematical relationship, or our flux, symbolized by phi b, is equal to our current I. I need to save this and reopen it because it's going to keep giving me that thing. So it is our current I multiplied by what is called our inductance L. So from this, Greek letter phi, so let me draw that less crappily, with a subscript b. So from this relationship, inductance can be defined as the ratio of the change in magnetic flux of an element due to a corresponding change in electric current. So we can say that L is defined as really the change in flux due to the change in current. So our units will be Webers, which is the unit of magnetic flux. I know you guys don't have the foggiest clue what that is, per amp, which is identical to a volt second per ampere, or 1 Henry. Henry is the classical unit of inductance. We are probably going to wind up using that volt second per ampere relationship a lot just to make sure that all of our units agree, since we are used to dealing in quantities of volts and amps and all that kind of good stuff. I honestly don't know. If I can actually go off on a small tangent here, I want to say that the guy that Henry is named after was an electrical engineer for Bell Laboratories. I'm not 100% sure on that, but I believe that to be the case. The unit of capacitance, which we are going to cover on next Monday, is called the farad, named after English physicist Michael Faraday. Now, what's crazy to me is that the laws of induction and how these things behave, which we are going to talk about in a moment, are called Faraday's law. So I don't have the foggiest clue why Faraday's law doesn't apply to the component that has units of farads. That's old dead white people from England made that decision well before I was born. Caitlin, did you have a question?
Is it just like the geometry of coiling the wires?
So a magnetic flux is going to exist. That's a fantastic question. A magnetic flux is going to exist technically any time that we have a magnetic field, because it's just the amount of magnetic field that passes through a particular surface. So if you think about it, if we have a long straight wire, the magnetic flux that coils around passes through a surface that is bounded by the perimeter of the wire extending out into infinity. So the flux is very, very small because the area that's enclosing the flux is extraordinarily large. But when we coil the wire, we are concentrating that flux into a very, very small area. And so we are seeing the effect of the magnetic field much, much more. Does that make sense? Yeah. So coiling of the wire doesn't really make flux. It's just the bounded area causes the flux to be much, much higher. Good question. All right. An alternative definition for flux, and this is where we're going to talk about Faraday's wire, or Faraday's law, excuse me. Alternative definition for inductance is the tendency of an electrical conductor to oppose a change in the electrical current flowing through it. And the mathematical relationship for this is what's known as Faraday's law of electromagnetic induction, where we have E, the electromotive force, is equal to negative the derivative of the magnetic flux as a function of time with respect to time. Now, we're never going to actually apply this equation in this class, although it is critically important to the entire concept of electrical engineering. It's calling me. All right. So I want to talk about this guy right here because there's a couple of important things here. Okay. And I want to tie it to something that, 1, 2, 3, 4, 5, 6, 7, 8, 9, roughly 10. There's some long-haired dudes in here as well, so maybe a few more may be familiar with. How many of you have ever dried your hair, blow dried your hair? Several people. How many of you have ever, with the blow dryer left running, unplugged it from the wall and seen sparks? Few people. That is electromagnetic induction, okay? What is happening there is the motor inside the hair dryer contains a large inductor, all right? there is a certain amount of current flowing through that inductor. And when you interrupt that current by unplugging the hairdryer, what happens is that that change in magnetic flux is very, very large, which winds up inducing a very, very large electromotive force. Well, if you recall from our second class, electromotive force, E here, is just a fancy word for voltage. So when we unplug that hairdryer, we're actually causing a huge difference in electric potential to come across the plug of our hairdryer, so large that it's ionizing the air and creating an electrical path between the prongs of our plug to try to keep that current flowing for longer. That is induction. Okay. Yes, ma'am.
Does the same concepts happen like when you go plug something in and it does the same thing?
So that is usually static reactions, and that's more capacitive in nature. He is correct because electromotive force is force per unit charge. So it is not a force at all. He is absolutely right. That's his bag of cats. All right, so let's talk about characteristics of an inductor, circuit characteristics of an inductor specifically. All right, so first thing that we should probably introduce is the schematic symbol. An inductor's symbol is coil of wire. Makes sense because that's physically exactly what it is. For those of you mechanical engineering types, it also looks like the schematic representation of a spring, which also isn't wildly off base. I don't want to get into the big bag of cats of how you can use electric circuits to represent simple harmonic oscillators and all that kind of jazz so that you can use circuits to do mechanical engineering and vice versa. But anyway, it's that particular schematic representation for a reason. Inductors obey the passive sign convention, which means that if we have a current IL of T flowing into the positive polarity terminal of our inductor, not ito, into we consider it to be absorbing power. And when current flowing into the negative terminal, we say that it is applying power. Okay. Now, what's interesting about this guy is it ain't a resistor. Okay. An inductor, because it does have a form of temporary energy storage, can actually supply power to the rest of the circuit. Okay, so it is not just simply converting electrical energy into heat. It is storing energy and then releasing it back into the system as is needed, depending on the type of system that we have. Okay. If we use Faraday's law of induction, we can find that the voltage drop over an inductor is the derivative of the magnetic flux with respect to time, which doesn't help us a lick, but recognizing that the flux depends on the current gives us this simple relationship. the voltage drop over an inductor is equal to the inductor value itself times the derivative of the current flowing through the inductor, okay? So we have introduced a calculus-based relationship into our circuit analysis. Terrible. So horrifyingly scary. It's actually not true. It's the relation, so that's a fantastic question. My short answer is Lenz's law, and when you get to physics 202, that will make sense. The long answer is too long for us to talk about. So you can ignore that middle relationship entirely for this class and be perfectly okay. So I hate to wave it away, but it's best to wave it away. Yeah, so Lenz's law is all about that opposition. So it changes. So we're seeking to keep the flux constant. So if we have a sudden decrease in electromagnetic flux, and the voltage tries to force the responding flux to go in the opposite direction. So that's where that negative sign takes care of itself there. All right, this relationship, which I'm going to put a 1 over here for, and I'm going to box in red. Is the first of exactly 4 equations that I'm going to expect you to learn. I did not say memorize, I said learn. Okay, as there's a distinct difference between those two things. Ooh, it's blowing me up. All right, so I want to talk about this particular relationship for a moment as well, because there are 2 very important things that we can glean from this relationship. All right. Number 1, let's say that we have a DC circuit that contains an inductor, such that the current that's flowing through the inductor does not change with time. What is the voltage drop across the inductor? 0, right? So if the current doesn't change, it doesn't matter the value of the inductance at all, L times 0 gives us 0 volts. So our first critical relationship here tells us that in a DC circuit, inductors behave like a short right? So for any DC circuit that we are analyzing, or let me rephrase that very slightly. For any circuit at DC steady state, which will become very important in about 2 days that we are analyzing, we can treat an inductor as if it were a short circuit and lose no information whatsoever. Okay, no voltage drop over it, which means it's not absorbing. Well, I don't want to get into that bag of cats, but no voltage drop over it. Treat it as a short circuit. What if our current tried to instantaneously change? So let me draw a picture here. Let's say that we have a circuit containing a current source like so. And then we had a switch. And our switch is initially connected to a resistor, and then at some later point in time, which I'm just going to call t is equal to 0 for right now, our switch instantaneously changes positions such that our inductor now sees all of that incoming current, okay? What would our voltage drop across our inductor look like? Exactly correct. So if an inductor were to be able to experience an instantaneous shift in current, meaning going from 0 amps of current to whatever this IS happens to be, that would require an infinitely large voltage drop to appear across the inductor's terminals. What does an infinitely large voltage drop imply? An infinitely large transfer of energy in an infinitely small amount of time, which cannot happen, right? So our second constraint here is that the current through an inductor cannot change abruptly. Let me be very, very clear about what I mean by change abruptly. The current flowing through an inductor needs to be a continuous function, effectively. So we cannot have let's say that this is our inductor current, IL as a function of time, like so. So we can't have it do this. Right? Actually, let me do this in red. Doing something like this, where it has the same, two different values at the same instant in time, breaks physics. Can't happen, right? Bad. But if we take that same basic thing and now we make that change, take a little bit of time, perfectly okay. Call this guy T1, let's call this guy T2. T2 minus T1 does not equal 0, we're okay. So that change can occur over a couple of nanoseconds and everything's fine, or even a couple of picoseconds and everything's fine. It just cannot be instantaneous, all right? So effectively, that voltage has to be constrained to be non-infinite. That's it. Okay, so we'll see when we're dealing with stuff that it might change, like we were talking about earlier, right? The current flowing through the inductance of the hairdryer. It actually takes us some small physical amount of time to unplug that hairdryer, right? So that's why we're not ripping a hole in the space-time continuum, because it takes us time to do things like that, right? So we're just making the physics behave with this constraint. Joy, I think you had a question? Okay. All right. So that is our first relationship up here in red. Our next mathematical relationship will come by simply manipulating this guy, all right? So we can get the voltage drop over an inductor as a function of the current flowing through it. Now let's talk about how we get the current flowing through the inductor as a function of the voltage drop over it. Right? So our second relationship is this guy. Inductor current, IL of t, will be equal to 1 over the inductor value times the integral from negative infinity to t of VL as a function of x dx, where x here is just a dummy variable representing time. So because I have time as one of the limits of my integration, it shouldn't be showing up inside my other stuff. IL of t. IL of t, let me rewrite this if it was confusing, I apologize. IL of t is equal to 1 over L times the integral from negative infinity to some later point in time of the inductor's voltage. Now, we don't necessarily know what was happening with the inductor at the beginning of time, or when dinosaurs roamed the earth, or as it turns out in engineering, infinity is probably less than a second ago with regards to how inductors behave, but we'll talk about that in a couple of days. So I can change this ever so slightly to be 1 over L times the integral from T naught, which is just some time where we knew how much current was flowing through the inductor, to T of VL as a function of time, derivative of time, plus IL at T naught. So what I'm doing here is I am including some past behavior of the inductor to understand what the present behavior of the inductor is doing. So we could say that an inductor has memory to some small extent, okay? So how the inductor is behaving right now in the present depends on how the inductor behaved in the past. And that is characterized by this equation with the inclusion of that initial condition, all right? So I'm going to put a box around this guy too. This is going to be equation number 2. And then we are going to look at something that kind of illustrates this. Let's say that I have the following circuit. I'm going to use a pulse waveform here that I'm going to describe to you in a moment. So I have just some voltage source, V of t, connected to some inductance L. And I want to know what my inductor current IL of t is. And graphically, let's say that L is 1 Henry. We'll make the math easy. And this is V of t as a function of time. So our voltage waveform is going to be 0 volts until we hit 1 second. Then it's going to jump up to, let's call it 10 volts. It's going to stay there for 2 seconds. And then it's going to fall back down to 0 and stay at 0 until the end of time. So effectively, what I am suggesting is we have an inductor connected to an outlet or something like that, flip a switch, and then flip the switch back. So we turn it on and then we turn it off. Let's see what happens. All right.
This is 1 inch and 3 inch.
Yes, 1 second and 3 seconds. Caitlin.
Is this kind of how pulse width modulation works?
So pulse width modulation is the switching the voltage on and off and all that kind of stuff in a very specific, with a very specific duration for the time. But I wouldn't say that the inductor is necessarily part of that. We're just doing something similar to that to illustrate a point here. Okay. So if we assume, and I'll write this down, IL at 0 is equal to 0 amps. I want to figure out what the current flowing through this inductor is doing, okay, as a function of time for all t greater than 0. All right, so let's walk our way through this. Our voltage source could be considered a piecewise function, right? So it's 0 volts from t is equal to 0 to t is equal to 1 second. It's 10 volts from t is equal to 1 second to t is equal to 3 seconds. And then it's 0 volts from t is equal to 3 seconds on to infinity. So mathematically, I have d of t is 0 volts for 1 second, less than t, less than 2 seconds, 10 volts for, sorry, that should be 3 seconds. No, that's not even remotely right. 0 less than 1. Sorry, brain fart. 10 volts for 1 second, less than t, less than 3 seconds, and then 0 volts again for t greater than 3 seconds. So my current then will also have 3 distinct parts. Okay. So for 0 less than t less than 1, IL of t is going to look like the integral, sorry, 1 over L, so 1 over 1 Henry times the integral from 0 to t is equal to 1 second of 0 volts dt plus our initial condition, which happens to be 0 amps. So our current is going to look like 0 over that interval. All right. So I'm going to plot this on the same graph. I'm going to do it in red. So over this interval, our current and our voltage match exactly. Ah, dang it. I'm trying to fit it all down here. I think I can make it work. For 1 second, less than t is less than 3 seconds, we now have IL is 1 over 1 Henry times the integral from 1 second to t is equal to 3 seconds. And that's going to be 10 volts times dt plus IL at 1 second, right? So at exactly 3 seconds, we have, let's see, 30 volts times 2 seconds divided by 1 Henry, right? If we put the limits on this guy, we looked at this guy at exactly t is equal to 3 seconds, we should see that, gosh, let's see, 10 times 2 over 1 is 20 amps, right? So it's going to go up. I'll do it up here. It's going to be at 20 amps. And I'm just going to say for the sake of argument that up here is 20 amps. And in between these 2 points should be pretty obvious to see if we didn't integrate it to a specific time value. that we would just have a linear relationship, right? So if we left this as a variable, we would just have 10 volts multiplied by time. So we have a slope of 10 volts per 10 volt seconds per amp, whatever. 10 amps per second, I guess, is what it winds up being, right? So we have a linear increase in the current. For t greater than 3 seconds, what we have is IL of t is going to look like 1/1 Henry times the integral from 3 seconds to infinity of 0 volts dt plus IL at 3 seconds, which is going to be actually a constant value of 20 amps. Like so. So the behavior of the inductor, the amount of current that's flowing through it, depends on that past value. So just because we turn it off by forcing the voltage drop across it to be 0, doesn't mean that it lets go of that current. It holds on to it. Now we'll see in practical circuits, it can't ever hold on to that current infinitely. And it's because the wire and the inductor itself actually has some small amount of resistance. And so that current will slowly get turned into heat over time. That's literally what we're going to be talking, our next big topic, transient analysis is all about, is how that mechanism occurs. But we can see here that our inductor is, our inductor's behavior from a current standpoint absolutely depends on how much current was flowing through it in the past. That is critical to understanding the nature of inductors. All right. Our next relationship is the power absorbed by an inductor. So it will simply be the inductor current times the inductor voltage, because P is always equal to I times V, doesn't matter what circuit element we're looking at. But we can express that voltage as, so this would be I of L times T times L di by dt, or L I times the derivative of I, right? So this is our power relationship. I'm going to underline the important bits here. So when I ask you this question on your next test, which is, I would say there's a 50% chance of you seeing this one and a 50% chance of you seeing the one related to capacitors. And it's because I make different versions of the test, and it'll show, one will show up on half and the other one will show up on the other half. I'm going to ask you about what equation can be used to calculate the power in an inductor, or the power that is absorbed by a capacitor. And so for half of you, that is both of the answers that I have underlined, right? It's always going to be I times V, always, always, always. And then we can additionally express that as only a function of the inductor current, which may be useful. Pardon? No. Power is equal to, P is equal to I times V is not Ohm's law. Ohm's law says that resistance is the constant of proportionality between voltage and current in a resistor. This ain't a resistor, Ohm's law ain't applicable. So there is a current voltage relationship, but it is not as succinctly summarized, right? P is equal to I times V is power by definition. L times IL of T times di by dt is specific to inductors. So With that, the energy absorbed by an inductor is simply the integral from negative infinity to some later point in time of the power absorbed by an inductor. And doing a little bit of math here, substituting in our relationship that we just developed, L times IL, DIL, IDT. I guess technically all of these T should be X's, so let me fix that. So notice here, since we have the derivative with respect to X, and then we're integrating with respect to that same value, or that same variable, I guess would be a better way to put it. Those guys are going to wind up canceling each other out. And so this is going to turn into the integral from the current at negative infinity to the current in the present times L IL X, sorry, keep botching this. Actually, no, I can do it as T now, sorry. IL of T, D IL of T. And under the specific assumption that the current flowing through the inductor way back at the beginning of time was 0, this reduces to 1/2 L times the inductor current squared. This is relationship number 4. So these are the 4 relationships, again, that I expect you to learn for the upcoming exam. There will be 4 extraordinarily similar relationships for capacitors that we will develop on Monday. The similarities between these two are astounding, and you will see why shortly, okay? So, gosh, I've been talking for almost an hour. All right, one or two last little things here, and then I will be quiet. Let us now talk about combining inductors. All right, so this is a circuit element. We might see more than one of them in a circuit. How can we simplify things? That's the question that we're answering here, all right? So let's say that we have a network that contains multiple inductors connected in series. So this is inductor L1. This is inductor L2. And this is inductor L sub n. Like so. And we have some voltage drop, V of t, over the network. And therefore we have some current, I of t, flowing through all of these inductors. We will get a corresponding voltage drop. Let's call it V1 of t across inductor 1, V2 of t across inductor 2, and Vn of t across inductor n. If we apply Kirchhoff's voltage law around this loop, we get V of t is equal to V1 plus V2 plus Vn. And we can relate all of those voltage drops to that common current I flowing through all of the inductors, such that we will have L1 times the derivative of I with respect to t plus L2 times the derivative of I with respect to t all the way out to L sub n times the derivative of I with respect to t. And since we have a common factor of the derivative of current with respect to time, this is going to look like L1 plus L2 plus L sub n multiplied by the derivative of current with respect to time. So we just used a bunch of math to say something pretty straightforward. Inductors in series add like resistors in series. Okay, we got to prove it. Can't just assume crap. Inductors in series, I don't want to even say add, combine. That's a better way to put it. So based on this, do I need to mathematically prove to you that inductors in parallel add like resistors in parallel? No. Okay, I'll shut up then. I will write down that sentence just to be clear. Exactly right. We would literally just use KCL and the integral based relationship and get the exact same result. All right. So that is enough out of me.